All right, question 2, we have the vector field f, which is y minus z, comma z minus x, comma x minus y, and s here is the cap of the sphere, x squared plus y squared plus z squared is equal to 16, above the plane z is equal to the square root of 7, and we're going to let c denote the boundary of s. All right, now here we'll assume that s is oriented downward, and the boundary curve c is given an orientation that's consistent with the surface S, and our job is to verify that the line integral and the surface integral of Stokes' theorem are equal. All right, so here is the cap of our sphere, and that's formed by uh, intersecting the sphere with this plane, z is equal to the square root of 7, and they intersect in this green boundary curve C here, right? This is a circle, and we note here that the normal vectors to our surface are pointing downward. So that means we're going to have to orient this boundary curve C clockwise as opposed to counterclockwise, because we have to follow that right-hand rule convention. And so if I curl my right fingers in the positive direction for C, my right thumb has to point in the general direction of the normal vectors. And so if they're pointing downward, right, then we have to orient this thing clockwise, right? If it was counterclockwise, then our right thumb would point upwards. Okay, so what about the radius of this boundary circle? Well, if I substitute in square root of 7 for z, I see that I have x squared plus y squared equal to 9. So this boundary curve here is a circle of radius 3, and we're orienting the circle clockwise. And so a parameterization for that circle would be 3 sine t, 3 cosine t. And since the circle lives in the plane z is equal to the square root of 7, the k component here is just constant root 7. And t will vary from 0 to 2 pi. So notice I've swapped the sine and the cosine, and that will give rise to a clockwise orientation as opposed to a counterclockwise orientation. And here's the derivative vector, r prime. All right, so now to compute the line integral over this boundary curve, okay, we are going to integrate this dot product of our vector field f evaluated along this circle, and we're dotting that with the tangent vector, right, r prime. All right, so now let's go ahead and punch all that in. So f of r of t, well here we're setting x to 3 sine t, y to 3 cosine t, and z to the square root of 7. And since our vector field f has for its I component y minus z, that means that f evaluated along the circle will have for its I component y, which is 3 cosine t, minus z, which is the square root of 7. Okay, and then likewise the j component, z minus x, that will be the square root of 7 minus 3 sine t. And then the k component, x minus y, that's going to be 3 sine t minus 3 cosine t. All right, and then we're dotting that with this tangent vector, which is 3 cosine t, negative 3 sine t, 0. So this dot product will come out to be as follows, right? We're going to get a 9 cos squared, and then minus 3 root 7 cosine t. And then for the j components, we're going to get a minus 3 root 7 sine t, and then plus a 9 sine squared t. And then from the k components, we'll just get 0 because of the 0k component on the tangent vector. All right, so now from the Pythagorean identity, 9 cos squared plus 9 sine squared, that's just 9. And then here I've just factored out the 3 root 7. So I have minus 3 root 7 times the quantity cos t plus sine t. And now if I integrate cosine t over the interval from 0 to 2 pi, I'm just going to get 0, right? Because that's sine t evaluated at these endpoints. That's just going to give me 0. And likewise for sine of t. If I integrate that, I'll get negative cos. And evaluating there and taking the difference, I'm going to get 0. So I'm just going to get something from this 9 here, and so the integral is 18 pi. All right, so that's the line integral over the boundary, and now our job is to compute the surface integral of the curl of our vector field over this cap, which is can be computed as follows, right? First, I'll go ahead and compute the curl. And so here, pretty straightforward calculation, and nicely it's a constant vector. So I have negative 2, negative 2, negative 2. So I just factored out that negative 2. And now for a parameterization of the cap of our sphere, Okay, I'm just going to use the sphere parameterization from the table in the surface integrals worksheet, and note here, right, the radius of the sphere is 4, so we're setting a equal to 4. And we do have to be pretty darn careful with the bounds here. Okay, so first off, the polar angle v, right, this is really just theta. That's going to vary from 0 to 2 pi, so that's straightforward. But u, which is the angle phi in spherical coordinates, this is a little more complicated in this case. So I've drawn this little cross section right here. So we're just looking at the cap of this sphere, right? The portion of the sphere that lies above this plane, z is equal to the square root of 7. And so the angle phi, or equivalently the angle u, right, that's going to vary from, well, 0 when we're along the positive z-axis out to this angle, which I'll call alpha, where what? Well, when we're at this uh, intersection point with the sphere and the plane, okay, the angle alpha that's going to be formed is such that this right triangle that I'm looking at, right, this has hypotenuse 4, that's just the radius of the sphere, because it's just the distance from the origin out to this point on the sphere. And then the height here, this is just the height of the plane, so that's the square root of 7. And then this right here, this is just the radius of uh, the boundary circle, C, right? So that's just 3. And you can also, of course, see that just from the Pythagorean theorem. Okay, so what is this angle alpha? Well, if I take the sine of this angle alpha, I'm going to get the opposite over the hypotenuse, so I'm going to get 3/4. So this angle alpha then is the arcsine of 3/4, which of course is not a nice unit circle angle. So I'm just going to call it alpha. And as we'll see in a little bit, fortunately, when we actually compute the integral, things do clean up pretty nicely. But instead of just carrying around the arcsine of 3/4, which is just kind of messy to write, I'll just call it alpha. All right, now we also have to be pretty careful here when it comes to the normal vector tu cross tv. So I'm just taking this straight from the table. Okay, again, from the surface integrals worksheet. Here, this is a squared sine u, and a is 4, right? And then I have my unit vector in the direction of my position vector r. So that's sine u cos v, sine u sine v, and cos u. And because the surface is oriented so the normal vectors are pointing downward, I do need to put a negative in front here. And the reason why is because this tu cross tv that you see in the table, right, without that negative, that thing, as we saw in the last section, that normal vector points outward, right, from the sphere. Okay, so for our tu cross tv that we're going to use in our computation, we need to put a negative in front. So you have to be very careful there when it comes to the orientation. All right, so now let's go ahead and set up our surface integral. So we are going to take our vector field, which is just this constant vector here, right, for the curl, and evaluate it along our surface S. And then we're going to dot it with this normal vector right here in blue. And we're going to integrate this dot product over this region R, which is really a rectangle in the UV plane where U varies from 0 to alpha and V varies from 0 to 2 pi. All right, so let's go ahead and put all of this in. So since our curl vector is constant, right, we're just going to get -2 times the vector 1, 1, 1 along the surface. And then we're dotting that with this normal vector in blue. All right. And as you can see, this is a little bit messy when you expand this all out. Okay, so a couple of notes here. The -2 times -16, so that's 32, and I'm just going to bring that out front. And then I'm going to go ahead and take the dot product. Now the sine u, right, is multiplying each one of these components. And then if I dot it with the vector 1, 1, 1, what am I going to get? Well, I'm going to get sine squared u cos v plus, and then sine squared u sine v, and then plus sine u cos u. All right, now these two terms right here have a common factor of sine squared u, so I can factor those out, or sorry, factor that out, the sine squared u, and that leaves us with the cos v plus sine v in parentheses. And so now what I'm going to do in this next line is split this up, because notice I'm integrating a product of something that depends only on u and the other factor depends only on v, and we're integrating over this rectangle. So I'm going to break that up as my integral of just sine squared u du from 0 to this angle alpha times the integral from 0 to 2 pi of cos v plus sine v, okay? And I have this other part too, which is the integral of sine u cos u, and this depends only on u, so the v integral is just going to contribute a factor of 2 pi. And the integral of sine u cos u is pretty simple. You could use a substitution if you like, or just note that cos u is the derivative of sine u, so you're going to get 1/2 sine squared u, and we're going to evaluate that from 0 to this angle alpha. All right, so now something really nice happens here. This integral of cos v plus sine v from 0 to 2 pi, just like we saw in the computation of the line integral. Right? If I integrate cos v from 0 to 2 pi, I get 0, and likewise for sine v. So this factor right here is 0, so I'm going to get whatever this integral is equal to, which I could compute, but I don't need to since it's being multiplied by 0. So this entire thing just drops out to 0. So I'm just left with this portion. The 2's cancel, and I get a pi times the sine squared of alpha. Now, what's sine squared alpha? Well, sine alpha is 3/4, so if I square the sine, I'm going to square the 3/4, and that's going to give me 9/16. So when all is said and done, I'm going to get pi times 9/16, and that's all being multiplied by 32, and that simplifies to 18 pi, just as Stokes' theorem promises. Okay, so a little bit messy of calculation here, but also, right, we have to be very careful when it comes to the orientation. Okay, we had to choose a downward pointing normal, and we also had to choose the appropriate orientation for the boundary curve, right, which is clockwise in this case. All right, well, that's going to do it for this problem. Thanks so much.